Hi there, my name's Kyle Purser, and I'd like to talk to you about Atwood Machines. Alright, first things first, let's talk about our learning objectives for today. So, you should be able to explain the physical situations involving the interaction of bodies using Newton's laws. Secondly, you should be able to analyze scenarios and make claims about the forces exerted on an object by other objects for different forces and components. And thirdly, you should be able to represent forces in diagrams or mathematically using appropriately labeled vectors with magnitude, direction, and units during the analysis of a situation. Now, you may be like, Kyle, what's an Atwood machine? Great question. Atwood machines were originally created in 1784 by George Atwood to verify mechanical principles of motion, Newton's laws, with constant acceleration, gravity. A big real-world example of these Atwood machines would be weightlifting machines in the gym. Weightlifting machines use weights connected by cables, connected to pulleys, where you push the weight and you work against gravity. It's two opposing forces which uses Newton's second and third laws. The video on screen is a great example of an Atwood machine in the gym. This real-world example shows us two opposing forces. One is greater than the other, so the bar comes down, and then the other weight goes up. On screen is yet another example. This one I actually set up myself. You see, it's not the same because one weight is hanging, but the other one is a cart on a track. This shows that not both weights need to be suspended for it to be considered an Atwood machine. Alright, so now we're going to create something called a free body diagram so we can depict the forces and components on these masses in the Atwood machine. So we're going to start with mass 2. So here we have mass 2, and we can see that mass 2 has a force of gravity and a force of tension. And now for mass 1. So mass 1 also has a force of tension. The force of gravity for mass 1 is less than the force of gravity for mass 2. This is because mass 1 is smaller than mass 2. So what does this mean in the Atwood machine? So that means everything is moving in the direction of mass 2, which is why we see acceleration here and here. Block 1 is moving up and block 2 is moving down, which means that the positive direction is down since the net force is moving with mass 2. Now, it seems a little weird, but technically, mass 1 is also moving in the positive direction. Because if we set it up like this, where we have mass 1, and then we have mass 2, we can see that everything is moving in this direction. And since mass 1 is also moving in that direction, these are both moving in the positive direction. Now let's look at a little bit of a different example. This is the example I just showed you. Now, this is a little different. So we have our cart, draw a little cart, and then we have our force of gravity. And now opposing our force of gravity, we have normal force. Now this is different because the other examples didn't have normal force since they were not on a surface. But this one does, and these two forces oppose each other and cancel out. But we still have a force of tension going this way because we have our string connecting these two masses. And then for a hanging mass, we have, just like the other ones, force of gravity, and then we have our force of tension. It's important to note that the force of tension is actually equal in both these masses. And if we set this up like the other masses, normal force and force of gravity, and these equal each other so they cancel out, and then we have force of gravity over here. And because these cancel out, everything has to move this way. So the net force is this way, even though this hanging mass weighs less than the cart. Because these two forces cancel out, everything moves in the direction of the hanging mass. Another important thing to note is that on here, let's say mass 1 and mass 2 had the same mass. Well, what do you think would happen? If neither mass weighs more than the other, then they're not going to go anywhere, because the force of gravity of mass 1 and the force of gravity of mass 2 are the same, which means there's no net force in either direction. And again, the force of tension is the same in both of these. So there's no net force in any direction, so they're just static. This is an example of Newton's third law in the hanging mass system. Now that same logic does not apply here, because since these forces cancel out, this mass is going to move regardless. Now, if this mass was heavy enough and the force of friction was great enough, then they would be able to cancel each other out. But in this example, we're assuming that there's no friction in the negative direction. The videos that you're seeing on screen right now are videos of the Atwood machine that I set up. You can see that despite the weights of the cart and the hanging mass both changing, acceleration always goes in the direction of the hanging mass, as we discussed before. And that about wraps it up. Thank you for watching, and if you're still confused or curious about Atwood machines, maybe you want to learn more about the masses or you need to clear some confusion, I would suggest going online to Google and searching up Atwood machine physics simulation or something along the lines of that. I've used physics simulations online before and suggest them to other people, and they serve as great learning tools and they'll clear any confusion you have. And with that said, thank you for watching and have a wonderful day.